In this dynamics lesson, we'll be learning about mass, weight, air resistance, and terminal velocity. These are the learning outcomes. Mass. Mass is the measure of amount of substance in an object. SI unit is kg. Another way to visualize what is mass is actually about the total number of protons, neutrons, and electrons in an object. So generally, the more numbers of protons, neutrons, and electrons in an object, the larger the mass. And mass of an object does not change unless you physically break it apart. So if you have an object that is 2 kilo and you split them into half, so this would contain 1 kilo and this would contain 1 kilo. One thing to note is that mass is not volume. A misconception is that when object is big, it has a lot of mass. If the object is big, it is actually just only meaning that it has a big volume or it occupies a lot of space. Space occupied does not necessarily mean that there is more substance. Take a look at this example. This object occupies quite a bit of space, okay, but it has only 9, let's say, particles. This object occupies little space, but it also has 9 particles. So actually both these two objects has the same amount of mass, just only that this occupies a lot more space as compared to this. Another misconception is that when object expands when it's being heated up, so mass changes when temperature of the object changes. But again, when object expands, what changes is actually the volume of the object or the space that it occupies. The amount of substance in the object remains the same, thus the mass remains the same when the temperature changes. Okay, let's move on to weight. Weight is a quantity that is related to mass, and generally the larger the mass, the more material it has, the greater the weight. Greater weight generally means it's more heavy or requires a greater force to lift it up. But weight is actually not equivalent to mass. Okay. The SI unit for weight is actually is Newton, and it is not kilo. Okay, this is one of the greatest misconceptions that students have. They think that weight is actually having a unit of kilo, but no. The reason is because in physics, weight is considered to be a force. So what is weight? Weight of an object is defined as the force acting on it due to gravitational attraction or gravity. So the difference between mass and weight. Okay, as summarized, mass SI unit is in kilo. Measure amount of matter in an object. It doesn't change when object is at different location. However, weight, your SI unit is in Newton, and it measures the magnitude of the gravitational force that pulls the object towards the ground and can change depending on the location of the object. So the weight of an object is different on Earth as compared to be on Moon. The gravitational force on the same object can vary at different locations as mentioned before. Okay, so you find that the gravitational force on Earth will cause an object to fall at an acceleration of roughly about 10 meters per second square. So it falls pretty fast. But the gravitational force on the Moon, which is weaker, will cause an object to fall at an acceleration of only about 1.6, so which is much slower. So you can say that object on Moon would fall very slowly as compared to Earth, as the Moon pulls the object towards the ground at a smaller force, or in other words, smaller weight. So objects on Moon will weigh less, but it also means that you can lift a massive object with ease on Moon, as it doesn't pull the object down with much force as compared to on Earth. But take note that whether on Moon or Earth, or for the same object, the mass is still the same, as there's no change in the number of substance or the number of protons, neutrons, electrons in the object. Weight has a formula that's similar to F net equals to ma, which is W equals to mg. Okay, so where weight, W is the weight of the object, m is the mass of the object, and g is the gravitational acceleration of the location of the object due to the gravity. and it is also known as the gravitational field strength. So how do we find the weight of an object on Earth and on the Moon? So you find that 100 kilogram object mass 100 kilogram would weigh about, on Earth is just mass times gravitational acceleration on Earth, which is equals to 100 multiplied by 10, and the answer is 1000 Newton. But on Moon, the same object would actually weigh only, if you apply the same formula, its mass is 100 multiplied by gravitational acceleration of 1.6. On Moon, it's only 160 Newton. So trying to show you that you need less force to lift up that 100 kilogram object on Moon compared to on Earth. Okay, you find that this gravitational acceleration is the same for all objects at the same location, meaning that on Earth generally is about 10, on Moon is 1.6. It implies that all objects will fall at the same rate regardless of the mass of the object. So it means that a feather would actually fall as fast as a hammer. Again, it seems that the above statement is totally different from what we observe on Earth. How can a feather actually fall the same way as a hammer? Okay, so right now we're going to show you a YouTube video. This particular video is actually this astronaut is conducting an experiment on the Moon. Okay, on one hand he's holding a feather, on the other hand he's holding a hammer. Let's see what will happen.
Well, in my left hand I have a feather, in my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the Moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
Okay, you notice that the feather and the hammer actually fall at the same time, but since it's on the Moon, they fall more slowly as compared to Earth. So a feather and a hammer is supposed to fall at the same rate, okay, by acceleration of 10 meters per second on Earth. But why doesn't it do that? It's because their motion is influenced by another force which is invisible to us, but we can feel it. This force is the air that is around us, actually creates air resistance which alter the motion of the feather, making it different from a hammer. But if we remove this air resistance, actually both objects will fall exactly the same way. This is another video for you to see. Okay, this is under having some air, so you realize that the feather falls slowly. But if it's in a vacuum, so just now you observed that the feather and a ball actually fall at the same rate. It's because just now it's under a vacuum jar, which means that all the air has been removed. So air resistance is a force experienced by a moving object due to the collision with air while moving. It has a special characteristic of becoming bigger as objects travel at a higher speed. So for example, if on a windless day when you walk, you do not feel any breeze on you. But on the same windless day, if you run fast enough, you experience wind blowing on your body. But it is actually not the wind or air that's blowing on you. It is because as you move faster, you collide with more air layers and you experience it as wind. So if the air is moving towards the man, as shown in the diagram on the left, so this is like the wind that is blowing on the man, or if let's say you have the air but the man is running through a layer of air, okay, the end result is the same because both air and man collide with each other, which is perceived as wind. So both will experience air resistance. Next, terminal velocity. Due to air resistance, an object undergoing free fall will increase its speed under the influence of gravity, but will eventually reach a constant speed. and this constant speed is known as terminal velocity. Since velocity is constant, it means that the object is under balanced force. And the balanced force comes from where the air resistance is this time so big that it is equal to the weight of the object. So this is the profile of the object as it increases its speed, and gradually it becomes the constant speed. So let's look at the first part. At the starting of freeform motion, the object is falling slowly at first. So the initial air resistance experienced by the object is low. Okay, so this is the diagram. You find that the weight is larger than air resistance. So the net acceleration downward is big, which means that the object rapidly increases its velocity as it falls, and is evident by the steep green box gradient. But as the object becomes faster and faster, the object's velocity becomes quite high in the middle of the freeform motion. Recall that the higher the velocity of the object, the higher the air resistance experienced by the object. So the air resistance experience is higher, and what will happen is that the blue arrow will increase bigger. But the air resistance at this stage is still lesser than its weight. So the net acceleration is still downwards but smaller. What it means is that the object will still increase its velocity but not as rapidly as before. So you can see, as in the gradient or in the yellow box, it becomes is becoming more and more gentler. Okay, at terminal velocity, the velocity would in this case the velocity was still increasing cause the air resistance to increase. The air resistance will increase till after being the same as the weight of the object. So you find that the blue line, the full forces will increase until the air resistance is exactly the same as the weight. So the net force in this case is 0. But one common misconception is that once net force is equal to 0, the object will stop. However, this is not true, because based on Newton's first law of motion, if the object is already moving and your net force is 0, you will still continue to move at a constant velocity. So in this case, the velocity right now remains constant and indicated by the dotted line, and this velocity is known as the terminal velocity. And notice that the red box is right now flat in terms of gradient, so the acceleration is equals to 0. So that's how you arrive at the terminal velocity of the object when it falls through. Okay, these are things that we use.